Good morning, everybody. It's a beautiful snowy day. Not as much snow as we have been getting, so that's okay. Although we need the moisture. We are ready finally to start calculus. I'm very relieved. I don't know where everybody is. Where is everybody? They should be here because I'm running a minute late. Hopefully they'll pop in a second. No days off in this class. So we're going to be covering the first part of chapter 2 today. We'll be talking about what calculus is and what it's used for, and then we'll be talking a little bit about limits. We'll be starting limits today. So limits is the first part. It's chapter 2. And then in chapter 3 and 4, we get into derivatives. And then chapter 5 and 6, we get into integration. So we cover all three of the basic calculus constructs this semester, but we focus a lot on limits and derivatives. And then in calculus 2, you focus a lot on integration. Okay, so let's go ahead and get started. And we'll talk about the different parts of what calculus is and what it is designed to do. Okay. So I'll hold off on taking roll for a minute or so, and hopefully the rest of them will pop in here. Let's see. All right. So one of the things that we want to talk about is what is possible and what's not possible in the world. There are always movies about traveling at what they call warp speed or whatever, where they travel faster and faster, right? So they can get to distant planets and galaxies. Not possible, okay? So back in 1905, when Albert Einstein was still a patent clerk, he showed that this was not possible, and he showed why it's not possible using the idea of the limit. So here's the formula that you've got down here for the mass of an object. And what he showed was that the faster you travel, the more mass you have. And so when you're looking at this particular equation here, m naught is your mass at rest. In other words, it's the amount of mass you have at rest. And then v is your speed, and c is the speed of light. So as your speed increases, now normally our speed is slower, obviously, than the speed of light. So this becomes a proper fraction, right? And then when you square it, it becomes smaller. And then 1 minus that is still positive. So we end up with our actual mass. Now, when we're traveling in a car, we're traveling so slow that the difference in our mass isn't really noticeable. But if you're traveling at much faster speeds, it is a little bit noticeable. You can feel it somewhat. And then as the speed approaches the speed of light, this fraction will approach the value of 1. But then as it approaches 1, you have 1 minus 1, which means you have 0 in the denominator. And you're not allowed to divide by 0. We're going to learn about why that is a problem and what it does to the fraction. Basically, what it does is as this gets smaller and smaller, the fraction gets larger and larger, so that the mass becomes infinitely large. And so your mass becomes infinite. And so there's a limit as to how fast you can travel, all right? So what is the idea of the limit? The idea of a limit is relatively simple. It is quite difficult to make precise, to make mathematically precise. but it's easy to explain as long as you allow a hand waving definition. We're going to do the formal definition in section 2.5, which is actually the very last section of chapter 2. And the reason is it's such a difficult definition that even though Gottfried Leibniz and Isaac Newton came up with the idea of the limit back in the late 1690s, they both understood intuitively what the limit was. It took another 140 years or so. It wasn't until the 1920s with Cauchy that we actually, Augustin Cauchy, that we actually got a formal definition of the limit. So they understood intuitively what it was. They knew it had to be true, but it took until the 1920s to get a formal proof of why a limit is what it is, which must, I mean, this should give you an idea of how difficult it must be. So it is probably the most difficult section in all of Calculus 1. And I've got some templates and some other things to help guide you through it. But the idea of the limit is simply this. If we look at this formula up here, and we allow the velocity to get larger and larger and larger without bounds so that it approaches the value of the speed of light. And then we have this 1 minus 1 in the bottom. What does the fraction approach? What value does the fraction approach? Is there one single value that the fraction approaches, or does it go to infinity? That's the idea of the limit. As you allow something to get close to something else, does it approach, does the y value approach some finite real number, or does it go to infinity or negative infinity? As x gets close to one thing, does y get close to something else? That's the idea of the limit. So as x gets close to 5, does y get close to one finite real value, or does it go to infinity? And there are all kinds of different possibilities there that we'll look at. Now, Gottfried Leibniz and Newton both simultaneously came up with the idea for calculus. In fact, Newton got there first, but he did not publish his results. He held on to his results and didn't tell anybody other than the British Royal Society about it. And then, so Leibniz actually published first, but they had the same idea, which is the idea of this limit. Caused a big hoo-ha, right? So at that time, the British and the Germans did not get along very well. And so it caused this big uproar with most of the mathematicians on the continent siding with Leibniz and all the ones in the British Isles siding with Newton. And what ended up happening was the British Isles went with Newton's notation, and the continent went with Leibniz's notation, which was bad for the British Isles because Leibniz's notation is the notation we still use today. It was pure genius. And it allowed the continent to kind of push ahead. I mean, they made huge bounds in mathematics while the British Isles was really slow to get traction. And this grudge lasted for 100 years. It took 100 years before the Brits finally agreed to use Leibniz's better notation. So yeah, never underestimate the power of a good grudge. Okay. So what we're going to be looking at is we're going to be looking at what's called the tangent problem and how to solve the tangent problem, as well as the instantaneous velocity problem. So that caused a problem as well. This is one of the ideas that held up the development of mathematics for centuries. I mean, keep in mind that when Newton and Leibniz came up with the idea of the limit, this really propelled everything forward just massively. You have no idea what a difference 100 years made between 1692 and 1792. We have the birth of the Industrial Revolution. We have all kinds of advances in medicine. We have just massive, massive leaps forward in almost all fields traced back to this development in mathematics. And then we're going to talk about the area problem, which was the third problem that had been holding up all of advancement for quite some time. So these ideas have been holding up the development of all kinds of things. So the two key ones were the tangent problem and the area problem. Physics was really held up by that instantaneous velocity problem. So it was sort of the third. So I kind of like to group it in there as well. So let's talk about the tangent problem and what differential calculus is. So when we're looking at the tangent problem, and we know what the slope of a line is, the slope of a line is rise over run. But the question is, how do we define the tangent to a curve? All right, so how do we talk about the rate of change of a curve as it is going along? So when we're looking at graphs right here, we have graphs with rate of change, okay? So when we're looking at these, we're talking about the rate of change of something. We're talking about how much y changes with respect to how x is changing. So this one definitely does have a rate of change. It has a negative rate of change of -2. We know that because the slope of the line is -2. And this graph in the middle has a rate of change of 1/2 because the equation has a slope of 1/2. So in other words, y is changing 1 vertically for every 2 that x is changing, right? This is the rate of change, all right? How much is y changing with respect to what x is changing? Now, the third graph over here is a horizontal line. It has no rate of change. In other words, the rate of change is 0 because y is not changing, even though the x value is changing, all right? But the problem is, on all of these, the rate of change is a constant, right? So on the far left graph, the rate of change is a constant -2. And in the center, the rate of change is a constant 1/2. And on the constant line, the rate of change is a constant 0. But that doesn't apply to something like x squared. So when you look at the rate of change of x squared and you want to describe how it's changing as you go from the left to the right, and I'm making it a little bigger so we can look at it. Think about how fast y is changing with respect to x as you move from the left side of the graph to the right side of the graph. So on the left side of the graph, it's really steep here, right? But negative. So the vertical change for every horizontal change is quite large. So again, we're talking about vertical change this direction compared to change that direction. So we do have a big change going on here on the far left. As it approaches the origin, though, the rate of change slows down. So it becomes less. Does everybody see that the y values are not changing as rapidly compared to how the x values are changing? And when you get to the origin, the actual rate of change at the origin at that one instant is 0. It's not changing there. And then on the right side of the graph, we've got a positive rate of change where the y value is going up a little bit for the x value going to the right a little bit. And then it gets faster and faster. The y value increases more for every move to the right the x value makes. So they have this problem of how to quantify how fast that rate of change was. So that was one of the problems that they had. So how do you measure the rate of change if it's constantly changing? And the answer is you use the slope of a secant line. So the slope of a secant line is a line that cuts through the graph at 2 points, and you can measure the rate of change by looking at the change between the 2 points on the graph. So when you're looking at this graph right here, you've got a f of a and x f of x. And if you're looking for the rate of change at the point A, as long as x isn't too far away, then you can measure the slope of this secant line, and you can use that to approximate the rate of change at A. Now, if it's way far away from A, then that's not going to be a good approximation. But if it's relatively close to A, it's a decent approximation. The closer the other point, x f of x, is to A, the better the approximation for the rate of change at A. What would be the best approximation for the rate of change at A? the exact rate of change at A. Anybody want to take a guess? No? Visualize, if you will, another line that cuts through here. That's a better, right? What else?
Is it tangent?
Yeah, it's the tangent line. If we take the tangent line at A, that represents the very best rate of change. And so you can see the tangent line coming through here as it gets closer and closer. The tangent line is going to barely skim the curve right there at A, right? And the slope of the tangent line becomes the best approximation for the rate of change at precisely A, all right? So the closer and closer the points are to A, the better the approximation, but that's using the secant line. Secant means to cut. So when you see this SEC, think of it as being part of the words like dissect, intersection, sect, section, vivisection. Oops, I can't get my eraser to work. All these things mean to cut up, all right? So when you think about the secant line is cutting across the graph. So it's cutting across the graph and at two different points. So when we think about the secant line, it's cutting through the graph, all right? Whereas the tangent line is skimming the graph at that one point. So the tangent line just barely touches at one point. And that would be this one right there, all right? And that would be the slope of the tangent line. So as we get closer over to it, here's the slope of the tangent line. So you can see the first secant line, which is here in orange, and then the second secant line provided a better estimation for the rate of change at A, and that's in that sort of teal color. But the best estimation for the rate of change at A is the tangent line that touches A, all right? So the slope of the tangent line to the graph at A measures the rate of change of the function at A. So that's up here. And we want to box that off to make sure that you understand it. So the slope of the tangent line is what's actually providing the measure of the rate of change at a particular point. This value is also called the derivative. So the derivative of a function at A is the slope of the tangent line at A, and we read it as f prime of A, and it looks like this, all right? So this is the derivative. And it's also the slope of the tangent line at A. Now, all of these things, Leibniz and Newton knew. They understood this, and this is what got them going on calculus, this idea. This is one of the three ideas that got them going on calculus with the limit, right? So as you'll find out, we're going to use the limit to define the derivative. So everything in calculus is defined in terms of the limit. The limit is really the basic building block of calculus. The idea of the limit, the concept of the limit is what allowed calculus to be developed. Without it, we would be stuck. So differential calculus is the calculus where we study derivatives and their applications. We spend a lot of time doing that in Calculus 1. So chapter 4 is all about applications of the derivative. We do a little of it in Cal 2 and a little bit more in Cal 3, but primarily the biggest section of it is done in Calculus 1. All right. Let's see if this one's going to work today. Sometimes it works and sometimes it doesn't. Yep. Okay. Not understand why when I move it from one screen to another, it gets way bigger than what it is. So here's the slope of the secant line. This is a link that's in your notes that you can kind of play with to kind of tell what the slope of the secant line is. Now remember, slope is rise over run. So we're measuring the vertical change over the horizontal change. And that's going to give us the slope of the secant line up here, which is 1.60. All right, and we're going to allow this to change and get closer and closer. So as you move this point right here, closer and closer to that one, do you see that it's approaching the slope of the tangent line? So we have a secant line right here. Does everybody see how it's cutting through both curves? To cut through is to be a secant line. But when I put this ball right on top of the other ball, it ceases to be a secant line and becomes a tangent line. So that's the tangent line right there. And that would be the slope of the tangent line. Now, let's see, delta x equal to 0. What does that mean? All right. So basically what we're doing is finding the slope of the secant line. This organization right here, mathinsight.org, has some of the best applets for playing around with concepts in calculus that I've seen. So if you've never seen it, you should bookmark mathinsight.org and you should look at some of their stuff. I'll probably bring it up from time to time. They also have a series that goes along with Cal 2 and Cal 3 that's excellent, all right? They have topics or pages for almost every topic, and they explain it, and they have interactive applets that you can play with to make the mathematics come alive more. So definitely bookmark mathinsight.org. Okay. All right, let's take a look at this first example. Example number 1. We want to estimate the slope of the tangent line, which is the rate of change, to a function f of x equal x squared at the point x equal 1, that's our A, by finding slopes of secant lines through 1, 1 and the point 5, 4, 25 sixteenths on the graph of x squared. So basically what we're going to do is we're going to approximate the slope of the tangent line with the slope of the secant line. All right, so we're going to take m secant, and remember that this is basically y1 minus y2 over x1 minus x2. This is just your old slope formula, right? So it's also written as f of x minus f of a over x minus a. So we have our points. So let's put the points back up here. We have the point 1, 1, which is on our graph. And our graph is f of x equal x squared. And then we also have the point 5 fourths, 25 sixteenths, which is also on that function. All right, so we've taken 2 points on the graph and we want to find the slope of the secant line connecting them. So we're going to take f of 5 fourths minus f of 1 over 5 fourths minus 1. F of 5 fourths is 25 sixteenths minus f of 1 is 1 over 5 fourths minus 1. All right, I need more space. So this is going to give me 25 sixteenths minus 16 sixteenths, get common denominators, 5 fourths minus 4 fourths, which gives me 9 sixteenths over 1 fourth, which gives me 9 sixteenths times 4 over 1, which gives me 9/4, which is 2.25, right? And that's my estimate for the rate of change. Now, what does that mean? That means y is changing 9 units up for every 4 units to the right that x is changing. Or y is going up 2.25 for every 1 to the right that x goes, right? So literally we're talking about the slope here, right? Now for the next 3 examples, we want to use the point 1, 1 and another point Q3 on the graph of x cubed. So when we think about the graph of x cubed, we can put up Desmos real fast. Whoa, okay. There we go. So there's the graph of x cubed. And we know that 1, 1, of course, is a point on it. Right? So there's the point 1, 1, and we're looking at the graph of x cubed right there. All right. So the next thing we want to do is complete the following table with appropriate values for the y coordinate of q and the slope of the secant line passing through the points P and Q. So our point that P is 1, 1, and our Q is going to change. Now it says 8 significant digits. I think that's a little bit of overkill. I don't think we need to go that far out, but let's see what we come up with. All right. So I'm thinking maybe I need a little more space in that column. Okay. So when x is 1.1, what's the y value? What do you get for the y value when you do that? What is 1.1 cubed?
1.331.
1.1 cubed. Yeah, 1.3331. And I don't think we need to write Q necessarily. We'll just leave Q off, and that will leave us more space to put in the slope of the secant line. All right, what about 1.01 cubed? I got that. Does anybody see a pattern developing here?
It's just gonna put zeros in the middle. Yep.
Yeah, and it's increasing the number of zeros between the 3, 3, 1. Does everybody see that? First, there are no zeros between the 3, 3, and 1. Then there's 1 0 between, then 2 zeros. Anybody want to make a prediction on the next one? There should be 3 zeros between the digits. All right, and that's what it means by 8 significant digits. How would we find the slope of the secant line? How would we do that?
Y, like the value we get, the y value we get -1 divided
Okay.
by the x value we're putting -1.
Yep. So this would be 1, it won't stay put. 1.33, okay, it's not going to stay put. Stop moving around. Okay, I know what I have to do. I have to take a picture of it. It won't stop moving. All right, that is the problem with using tables instead of pictures. They want tables for accessibility, but they don't work too well when you're trying to write on it. Oh, of course. There we go. All right. So now we've got our picture. Hold the picture up. Okay. So we should have 1.331 minus, and remember our P of XY is the 0.11. And Q of XY is basically this ordered pair right there, right? That's Q of XY. So we have 1.331 minus 1 over 1.1 minus 1. All right, the X value minus the X value of the other one. Make sure when you're doing this that you line them up coming out of the same ordered pair. So this is going to give me 0.331 over 0.1, which is about how much? So I will let you guys do the number crunching. This is 1.003003001 minus 1. 1.001 minus 1. 0.030030001. 0.001. And I think this one I'm just going to write the value. All right, so what do these come out to be roughly? 0.331 divided by 0.1 is 3.31, right? What about the next one?
Just add 1 0 in the middle, like 3.0301, and then just continue.
0.0301, and then what was the next one? 3.00.
Yeah, 3 and 0 0.
01, and then this last one, then following that pattern will be 0.0030001. All right, somebody give me a value for what you think it's approaching as it gets close to 1. What would you guess the slope of the tangent line would be there?
3.
I would guess 3, right? Let's try it by looking over here. We'll write the equation of the tangent line by doing y minus the y value at the point, which is 1, equals slope of 3 times x minus the x value at the point, which is 1. Does that look tangent to you guys? If we blow it up, does it appear to skim the graph, or does it look like it touches the graph and skims off of it? It looks pretty tangent to me. That looks really tangent to me. So I think that's probably a good estimate for the value of the tangent line right there at the point 1, 1. Now, how did I get the equation of the line there? I took the y minus y1, the point right here, which is 1, 1. We'll label it. So I took the 1 from the point and the 1 from the point, and then I used my estimated slope of 3. That's the point slope form of a line. Y minus y1 equals slope x minus x1. That's what I did to get the tangent line. And we're going to be doing that all semester. All right. Okay. And as it turns out, that is the slope of the tangent line. That is the tangent line. It truly is tangent at that point. We did find it. That is the real value. It will take us quite some time to get to the point to where we can find it quickly and easily, because finding a table is not fast, is it? I mean, this table was not fast. That took a long time. There are faster ways of doing it that we will learn, all right? So example 3, of course, is to guess the slope of the tangent line, which we did, and then to write the equation of the tangent line. So again, we took the point 1, 1, and we took our estimated slope of 3, and we wrote it in point slope form of the line. So those of you who are confused by how I got that equation, this is y minus 1 equal the slope, which is 3, times x minus 1. So this is x1, y1, and this is our slope, right? And that's how we got it, right? So this is the first problem that was causing a lot of difficulty in mathematics, physics, science, all kinds of fields. They couldn't quantify the rate of change very well. So they were trying to come up with the idea of the limit. And that's what Leibniz and Newton simultaneously came up with. Well, Newton got there a little first. Okay.
So I'm not exactly sure where you're getting the 3 for the slope from. I don't
I'm just
follow.
guessing. So I'm looking at the numbers 3.31, 3.031, 3.003001, 3.00030001. I'm guessing the next one would be 3.4 zeros and a 3, 4 zeros and a 1. It looks like it's going to get closer and closer to what we would call a limiting value of 3. It's getting closer and closer to 3. It may not ever get to 3, but it looks like it's getting close to 3. That's the idea of the limit. What is it getting close to? All right. What does the value look like it's approaching?
So
And
the
it
3
looks
is the slope of which graph?
the
It's
tangent line.
Okay.
The 3 is the slope of the tangent line, this graph in green that you see here. Okay, let's move on to the next problem that caused problems. This is the one that really confounded physicists for a long, long time, centuries, and held up things tremendously. And this is the instantaneous velocity problem. It's actually the tangent line problem. It is the same problem, just in a different format. So we know, for example, if we travel 140 miles in 2 hours, what is our average speed? What would it be? I'm going to start calling on people, wake you guys up. This is calculus. You got to be awake. Jack, how much?
70 miles an hour, right?
Yay. Okay, Jack's awake. All right, we've got one awake person at least. All right, so yeah, 70 miles an hour, 140 miles in 2 hours is the average of 70 miles an hour. The problem is, exactly what speed were you going after 1 hour, 10 minutes, and 43.25 seconds? I don't know, right? I have no way of knowing that. I know the average speed, but your speed varies, right? You get behind a slow car, you slow down. You need to pass somebody, you speed up. So your average speed is going to be different at any point in time than your instantaneous speed. So the instantaneous speed is different than the average speed. And that's what we're trying to figure out right now, is what is the average speed compared to the instantaneous. Well, we have a problem. So average speed is the change in distance divided by the change in time, right? That's the average speed or average velocity. So coming down here, here's your formula for the average speed right here. And this really should be speed, not velocity, although if we're using S, we can do it that way. This is going to be the change in distance over the change in time. What does physics use as a symbol to represent change in? Physics has a symbol for the words change in because it uses them so often. I think Juan
Is it
just,
delta?
yeah,
The
Juan just
triangle?
drew it in the air. The triangle, it's delta. So another way of writing this would be delta distance over delta time. And this is an uppercase delta, by the way. All right, that's the uppercase letter for D. All right. So we're looking at this, and the question is, what is the average speed? Well, it's just the change in distance divided by change in time. But doesn't that look like something else that we just did? I mean, what formula does that look like? We just did it.
Velocity?
Slope.
It's the slope, right? It is velocity, but it's the slope. It's the slope of the secant line. So this is the slope of the secant line. And that gives you average speed. All right. So you take your entire trip from the beginning to the end, you connect the beginning to the end, that forms a secant line. And then you divide the change in the distance by the change in the time. And that's the slope of the secant line. The problem is instantaneous velocity. So let me take a look at one of the pictures. Right here. If I were looking at this graph again, and this represented distance with respect to time, and I connected, this could be the beginning of my trip and the end of my trip, and then the secant line would represent my average speed. But the problem is, what if I wanted instantaneous speed? If I want instantaneous speed, I want the slope of the tangent line at that point. But the problem with the formula is beginning or ending distance minus beginning distance, ending time minus beginning time. And if I'm talking about instantaneous velocity, how much time has elapsed? If you're talking about instantaneous speed, how much time has gone by?
No time.
No time, zero. Cherie's right. 0 time has gone by. No time at all. In other words, it's 0. All right. So we've got 0 time passing by, which means we'd be dividing this formula right here by 0. Are you allowed to divide by 0? No, thou shalt not divide by 0 ever, ever, ever. Why are you not allowed to divide by 0? We're missing a lot of people today.
It's undefined and we can't do anything with a zero denominator.
Yep, and why? Does anybody know why? Okay, here's when we say undefined, what we're really saying is math is based on 10 basic ideas, and it is. There are 10 ideas on which all of mathematics is based. They're the foundation. They are assumptions. They are not things we can prove. They are things that we say, if we accept that these 10 things are true, then all the rest of this flows from those 10 things. And they're simple things. They're not hard things. For example, what is a plus 0? A. What's a times 1? A. What is a plus a negative a? 0. What is a times 1 over a unless a is 0? 1. That rule right there, that rule has as part of it, thou shalt not divide by 0. So our mathematics is based on 10 simple ideas, basically the additive identity, the multiplicative identity, the commutative property, the distributive property, the associative property. That's it. Those 10 ideas form the foundation of our mathematics, but one of the 10 includes you can't divide by 0. So when we say it's undefined, we mean it's not, it's our assumption that we won't ever do that, so we can't. All right. So we can't violate one of those 10 basic assumptions. That's why you're not allowed to divide by 0, and you never will be in our system of mathematics. Now, as a graduate student, you can create your own system of mathematics where division by 0 is allowed, but then all bets are off, right? You have to start over at the foundation, right? And in that system of math, who knows what 1 plus 1 might be? It might not be 2, all right? So basically, thou shalt not divide by zero caused big problems on the instantaneous velocity front because they couldn't divide the secant line by zero. And this like held up physics for hundreds of years. I mean, I'm not exaggerating when I say it held it up for hundreds of years. It really did. All right. So the problem was they had to come up with what they call the limit. The limit is the idea that you get close to zero, but not quite at zero so that you can find the value of it. That's the idea. You get close to zero, but you don't get to zero. All right. So that's the idea. But in the meantime, what they did was they did the same thing that we've been doing, which is to estimate the instantaneous velocity by using the secant line at a point very close by. So this is the same basic graph. This is t cubed instead of x cubed, but it's basically the same graph. And we want to estimate the instantaneous velocity at t equal 2 by computing the average velocity over the interval from 2 to 2.2001. So we're looking at a time and distance scale here at 2, and then we want to look at 2.001, and then we want to find our V average, which is approximately V instantaneous at t equal 2. All right, because we're not far away. So V average is going to be S of 2.001 minus S of 2 over 2.001 minus 2. So we need to figure out what this value is right here. When I cube 2, I get 8. So I know that one's 8. What happens when I cube 2.001? I don't know. Ooh, okay. I wasn't expecting that. 8.012006006,001, and I don't know if it keeps going or not. So I've got 8.012006001 minus 8 over 2.001 minus 2. So basically, I'm going to subtract 8 from this. So I get 0.012006,001. And I'm going to divide that by 0.001. And this is my average velocity over that very short interval, which should give me my instantaneous velocity. I got 12.006001. What would you guess the instantaneous velocity to be? Does anybody want to make a guess?
12?
Probably 12. I mean, I can't guarantee that, but probably 12. And how could we check it? Well, we could take the point 2.8 and we could write a slope of the tangent line and see if it fits with 12. All right. So we can do y minus 8 equals 12 times x minus 2. It's the same graph, so let's graph it. So y minus 8 equal, what did we guess? 12 times x minus the x value, which is 2. Uh-oh. Is that it? And I want to graph the point 2.8. Where's my?
Can you
Have
raise the
to
green
zoom
one?
out
It's
a little
just
bit.
tripping me off.
Oh, yeah. What do you think? I'll take the green one off so it doesn't confuse us. That looks pretty close. It's got to be darn close. It's really hard to tell, but it looks pretty close, doesn't it? All right. And what we're going to be learning over the next few weeks is how to get that exact without having to go through this guess and check of doing the slope of the secant line. Because filling out a table and having to guess the value is not a good way to do it. And that's what they've been doing for hundreds of years. And Leibniz and Newton both said there's a better way, and it's called limits. All right. Now, what's the third problem that held up mathematics and the development of all kinds of science and medicine for hundreds of years? This is the area problem. And this one actually confounded mathematicians, not for hundreds of years, but for thousands of years. And you have to keep in mind that when we study mathematics today, we're really studying Western mathematics, the history of Western mathematics. We are not taking into account Aztec mathematics, Mayan mathematics, Indian mathematics, or Chinese mathematics. Some of those civilizations had solutions to these problems long before Western mathematics had them. But because those civilizations disappeared before the printing press and before the written word became more permanent, we don't know as much about them. But it is true that the Aztecs down in Mexico had a rudimentary form of calculus thousands of years ago. So did the Chinese. So did the Indians in the Indus Valley over there in the Far East. So keep in mind that mathematics has been developed and lost over the centuries. Who knows what civilizations had it before those? But here's a problem that the Chinese were especially adept at solving. The Chinese and the Indians in the Indus Valley, which is how do you quantify exactly how much area is under a curve? This was the third problem. So how do you quantify the slope of the tangent line? How do you make the rate of change exact? How do you make the instantaneous velocity precise when your change in time is 0? And how do you find the precise amount of area under a curve? Not estimate it, find the precise value. This was the third problem that the limit solved. Now, there were all kinds of methods that were used to approximate to a high degree of accuracy the area under a curve. And this is the one that we'll be using later this semester, at the end of the semester in chapter 5. This is called a Riemann sum for Gerhard Riemann, who is the Western mathematician who came up with this method of finding the area under a curve. But he based it on the earlier work done by the Chinese and by the Indians in the Indus Valley and the Aztecs. Well, he probably didn't know about the Aztecs, but we know about them today. They did have quite advanced mathematics, as did the Mayans. We know less about the Mayan culture than we do about the Aztecs. We know relatively little, though, about either one. Not much of their written stuff has survived. So looking at this, what they did was they drew rectangles that just fit under the curve, and then they would take the area of the rectangles and add it up, and that would be an approximation. The smaller the rectangles, the better it fit the curve, and the better the approximation was. Does that make sense to everybody, how you'd get a better approximation if you used smaller rectangles? Okay, so the larger the rectangles, the worse the approximation. The smaller the rectangles, the better the approximation, but the more work you had to do. Now, studying limits of this type is what's called integral calculus. And this is what we'll study at the end of the course in chapters 5 and 6, and what you'll spend most of Calculus 2 studying. Calculus 3 takes what you've learned in Cal 1 and Cal 2 and expands everything into 3 and more dimensions. So in Cal 1 and Cal 2, we pretty much stay in the plane, 2 dimensions, X and Y. In Cal 3, we take all that knowledge and we go into the real world, where we have an X, Y, and Z, or an X, Y, Z in time, where we have multiple dimensions, right? So we apply everything to all those dimensions, right? Okay, so let's estimate the area between the X-axis and the graph of x squared plus 1 over the interval from 0 to 3 by using the 3 rectangles shown here. So we're looking at this one. Now, this is a terrible approximation. Does everybody see it's not a great approximation? I mean, this is too much area here and here. So it's going to be an overestimation. But all you have to do is take the width of each box, which is 1, and multiply by the height of the box. So I have 2 times 1 plus 1, 2, 3, 4, 5 times 1 plus 5, 6, 7, 8, 9, 10. 10 times 1. And add those together. 2 plus 5 plus 10. So the area is about 17 squared units. Right? And that's all we're talking about, just doing that right there. Knew I missed somebody. Uh-oh, I missed somebody else. Who am I missing? No. David's not here. Roz isn't here. Chelsea's not here. Aubrey's not here. And Dagger's not here, right? Okay. All right. I think I've got all of that then. Okay. And that's basically it. All right. We're ready now to start the next section, which is section 2.2.